let's take a look at vectors in two-dimensional space. I'll try and stay color-coded here. So let's say our first vector is vector A, and it's over 3 and up 4. So that's a vector in component form versus a vector with magnitude and direction. What that means is from the origin, I go over a positive 3, and I go up a positive 4, and that puts me right here. So that vector there is the same as that vector. You could write it that way, or you could write it as a coordinate 3, 4. That's called a position vector. Or you could turn it into a magnitude and direction and say that 3 squared plus 4 squared is equal to 5 squared. So you could call that same vector A 5 units at an angle of, we'll have to figure out how far it is off of the x-axis. So I could do tan of theta is equal to 4/3, or arctan of both sides, theta is equal to arctan of 4/3, and I think that's 53 degrees. So all different ways to represent a vector, but right now we're just looking at component form. And then if I had a second vector, vector B, and let's say vector B is negative 2i plus 6j, that would say I'm over negative 2. So that negative is giving me direction. It is up 6, and I go from the origin to the tip of that. So there's my red vector, vector B. There's my blue vector, vector A. Before we were adding them together with the tail of tip method and then drawing a resultant vector. But now if I just want to add those two vectors together in component form, it's really easy. Vector A plus vector B is going to be equal to the horizontal components added together. 3 plus a negative 2 is 1i. 4 and a 6 is 10j. And that's your answer. And you could kind of see that if I were to draw this out tail of tip. This green vector would be over 1 unit and up 10 units. If I want to subtract vectors, it's just as easy. A minus B. Probably the best way to do A minus B is to go just subtract the components. 3 minus negative 2 is 5i. 4 minus 6 is negative 2j. So that's how easy it is to subtract them in component form. This notation right here is the magnitude of the vector. So that is not a vector. It's only asking for the magnitude of it, which is the overall length. And I know that's going to be equal to the square root of the components, 3 squared plus 4 squared. Right, just like a right triangle, 3 squared plus 4 squared. 9 plus 16 is 25. Square root of 25 is 5. So the magnitude of vector B is going to be equal to square root of negative 2 squared plus 6 squared, or the square root of 40. So a unit vector is defined as the vector itself divided by its magnitude. So a unit vector is the vector itself divided by its magnitude. So I'm going to take vector A, 3i plus 4j, and divide it by its magnitude of 5. So that's going to give me 3/5 I plus 4/5 j. And what that unit vector is saying if it is exactly 1 unit long, so it's exactly 1 unit long, how far does it travel in the horizontal and how far does it travel in the vertical? So 3/5 is a decimal equivalent of 0.6. So it would be 0.6 over and then 0.8 up. So when that vector, vector A, is 1 unit long, it would travel that amount in the horizontal and that amount in the vertical. Unit vector is really useful because if you're asked to find a scalar vector, you could figure out the unit vector first and then just multiply it by a scalar. So if you know your planes unit vector with the wind, and then now you're going 600 miles per hour, you could just take that scalar of 600 and multiply it by the unit vector. So let me just say a few things about a scalar first. A scalar is just a number in the front of the vector. So if I want to find 3a, what that's saying right there is find 3 times the magnitude of a. I just take that scalar and I distribute it through that vector. So 3a is equal to 9i plus 4 times 3, 12j. So a scalar is a number out front. That magnitude, that increases the magnitude by 3. If I had a vector like, or if I had a problem like find 2a plus 3b, I would do those scalar multiplications first, and then I would add those two vectors together. So 2a would be 6i plus 8j. 3b, 3 times negative 2 is negative 6i. 3 times 6 is 18. So there's my 2a vector. There's my 3b vector. Then I add them together to get a 0 horizontal component and 26 vertical component. A plus b, I just take those components. So I'm on number 1. A plus b is going to be 9i plus 2j. Number 4, that's a scalar of 5. So I just take 5 and multiply it through here. It's asking for a resultant vector. So 5b will be 35i minus 15j. So on number 7, I'm going to do a minus b, 2 minus 7, negative 5i. 5 minus negative 3, 8j. So that vector right there is vector a minus b. And then the magnitude of that vector is going to be negative 5 squared plus 8 squared, or the square root of 89. So first thing I'll do is find the magnitude of b. The magnitude of b is going to be equal to the square root of 7 squared plus 3 squared, or square root of 58. So that's the magnitude of vector b. The unit vector of b is in 1 unit is going to be vector b divided by its magnitude, 7 over root 58. Whoops. Over root 58. I minus 3 over radical 58j. So there's my unit vector of b. So that would be the answer for number 12. So I just multiply that 8 through that quantity to get 56 over radical 58i minus 8 times 3, 24 over radical 58j. I'll go tangent of theta is equal to the opposite, 2 over 5, or the second tangent of 2/5. Now blue is 22 degrees. And then I'll find this red angle there. The opposite is 7, the adjacent is 1. So that's going to be second tangent of 7 divided by 1, or 82 degrees. So this red angle is 82 degrees. So the answer to number 17 is, what's the difference between those two vectors? The angle between those two vectors? 82 minus 22 will give me this angle right here of 60 degrees. 10, 2 here. And you can see these are exactly the same thing, except for rather than just have a x, y, now you have a third coordinate z. And if it was only 5, 9, that vector would be equal to 5i plus 9j. But now that I'm going in a three-dimensional space, I'm going to add a third component coming out from the board of depth, and that's going to be equal to 6k. I go over in the x direction 5 units. I go up in the y direction 9 units. And then I come out right here 6. But I can't really draw that on a board. So I got to put my third axis down here, labeling it z. And to show that I'm out here 6 units, is I have to draw a box. And the key to drawing these boxes is that the lines stay pretty parallel. So this line is parallel to this line and the same length. This line parallel to that one. This line here, whoops. And then this line is parallel to that one. This goes to here at 5 and out to there. So I go over 5 in x, up 9 in y, out 6 in z. And what that vector looks like in three-dimensional space is it goes from the origin to the very outside corner of that box. So that red line there is 5i, 9j, 6k, or is a position 5, 9, 6. The three-dimensional Pythagorean theorem works exactly the same as the two-dimensional one. If I want to find the length of this blue line here in the bottom of the box, I could see it's actually a right triangle with a length of 5 and a length of 6. So this is 5 squared plus 6 squared equals square root of 61. And then here's another right triangle right here. And in this right triangle right here, the height is now 9. So I go root 61 squared plus 9 squared equals my hypotenuse squared. So square root of 61 squared plus 9 squared equals that red line squared. So 61 squared is 61 plus 9 squared, 81, and then the square root of that. So the length of that red line is the square root of 142. Square root of the x value squared plus the y value squared plus the z value squared. So it's the exact same thing as the Pythagorean theorem in two-dimensional space, except for now it's in 3D space.